Since the dawn of the space age, humanity has been captivated by the cosmos. We've sent probes to distant planets, rovers to explore alien landscapes, and even humans to walk on the moon. But our quest to explore the universe comes with a cost: the environmental impact of rocket launches. Every time a rocket blasts off, it releases harmful pollutants into the atmosphere. These emissions can contribute to climate change, deplete the ozone layer, and pollute our air and water. As space exploration intensifies, it's crucial that we understand and address the environmental consequences of our celestial endeavors. Join us as we navigate this complex issue, seeking ways to ensure that our thirst for cosmic discovery doesn't come at the expense of our planet's health. The dream of space travel has always held a powerful allure, igniting our imaginations and inspiring generations. However, as we venture further into the cosmos, we must confront the reality that our cosmic ambitions have earthly consequences. The act of launching a rocket releases chemicals and particles into the atmosphere, contributing to environmental problems. The cumulative effect of frequent launches, particularly as the space industry grows, is a cause for concern. Ignoring these environmental consequences is not an option if we want to ensure a sustainable future for both humanity and our planet. As we stand on the cusp of a new era of space exploration, it is imperative that we prioritize environmental responsibility. In the realm of rocket fuels, unsymmetrical dimethylhydrazine, or UDMH, stands out for its potency and peril. Dubbed Devil's Venom, UDMH has powered countless rockets into space, but not without leaving a toxic legacy. This highly corrosive and carcinogenic compound has contaminated soil, water, and air at launch sites around the world. While Western space agencies have largely phased out UDMH, its legacy continues to haunt regions where it was extensively used. The Proton rocket, a workhorse of the Soviet and later Russian space programs, relied heavily on UDMH, leaving behind a trail of contamination. Despite its known dangers, UDMH remains in use by some spacefaring nations. However, the push for cleaner and more sustainable rocket fuels is gaining momentum. The vast expanse of the Kazakh steppe, once a pristine grassland, now bears the scars of decades of UDMH contamination. The region surrounding the Baikonur Cosmodrome has become a stark reminder of the hidden costs of our cosmic ambitions. For over 6 decades, Baikonur served as the primary launch site for the Soviet and later Russian space programs. But beneath the veneer of progress lay a silent environmental catastrophe, as countless tons of UDMH seeped into the soil and water. The impact on the Kazakh people has been devastating, leading to a range of health problems. The environmental disaster unfolding in Kazakhstan serves as a stark warning to the rest of the world. The quest for cleaner and more sustainable rocket fuels is driven by the need to mitigate environmental damage. Scientists and engineers are exploring promising alternatives, aiming to develop fuels that minimize their impact on the environment. One such alternative is RP1, a highly refined form of kerosene that is less toxic and produces fewer harmful emissions. RP1 is already in use by several launch providers, demonstrating its viability as a cleaner alternative. However, RP1 is still a fossil fuel and contributes to greenhouse gas emissions. Another promising avenue is the development of liquid hydrogen as a rocket fuel. Liquid hydrogen, when burned with liquid oxygen, produces only water vapor as a byproduct. While liquid hydrogen presents logistical challenges, it holds immense potential for reducing the environmental impact of spaceflight. Solid rocket motors, those colossal pillars of fire, are a spectacle to behold. Yet, behind this display of technological prowess lies a cloud of uncertainty about their true environmental cost. Solid rocket motors burn with an untamed ferocity, releasing a complex cocktail of exhaust products into the atmosphere. Among the most concerning components are hydrochloric acid and aluminum oxide. These compounds can react with atmospheric moisture to form acid rain, impacting sensitive ecosystems. The sheer volume of particulate matter released has raised concerns about its potential impact on Earth's climate. These particles can scatter and absorb sunlight, potentially altering the balance of incoming and outgoing radiation. While the precise nature and magnitude of these effects remain uncertain, the potential for significant climatic consequences cannot be ignored. The specter of acid rain looms over the enterprise of space exploration. Hydrochloric acid, a byproduct of solid rocket motors, dissolves in atmospheric moisture, forming acid rain. Even slight alterations in the pH of rainwater can have detrimental effects on sensitive ecosystems. Aquatic life, particularly in lakes and streams surrounding launch sites, are particularly vulnerable. Acid rain can leach heavy metals from soils, further contaminating water sources. Terrestrial ecosystems can also suffer from acid deposition, leading to soil acidification and nutrient depletion. The potential for long-term ecological damage is a serious concern. The ozone layer, Earth's shield against harmful ultraviolet radiation, has been a focal point of environmental concern. Solid rocket motors release chlorine compounds into the stratosphere, contributing to ozone depletion. Studies following space shuttle launches revealed the formation of transient ozone holes. These temporary depletions raised concerns about the cumulative impact of frequent launches on the ozone layer. Quantifying this impact remains a complex scientific challenge. The potential for even temporary ozone depletion to increase ground-level UV radiation warrants careful monitoring. Further research is needed to understand the long-term impact. As we delve deeper into the environmental consequences of solid rocket motors, we encounter a realm of scientific uncertainty. The complexity of atmospheric chemistry makes it difficult to fully grasp the long-term impacts. One pressing unknown is the fate of aluminum oxide particles released by solid rocket motors. These particles can linger in the stratosphere, potentially influencing Earth's climate. The long-term consequences of hydrochloric acid on stratospheric chemistry are not fully understood. The lack of comprehensive data on the composition and distribution of solid rocket motor exhaust hinders our understanding. Developing more robust monitoring systems and conducting long-term studies are essential. Our understanding of rocket launch's impact on the environment remains incomplete. Despite decades of space exploration, the data we possess regarding the precise composition of rocket exhaust and its long-term effects remains sparse. This lack of comprehensive data stems from technical challenges and the historical emphasis on mission success over environmental monitoring. The absence of robust data sets hampers our ability to assess the true environmental costs of rocket launches. Without a clear understanding of the specific pollutants released, we are essentially flying blind. As the frequency of launches increases, the need for a comprehensive understanding of the environmental consequences becomes ever more pressing. Section 2. The Illusion of Knowledge, Assumptions and Extrapolations. Our understanding of rocket launch's environmental impact often relies on assumptions and extrapolations. Scientists model atmospheric processes, but gaps in data introduce uncertainties. We often extrapolate from industrial emissions, comparing power plants to rocket engines. However, high-altitude conditions differ significantly. Rocket exhaust behavior in the upper atmosphere is unique. The diversity of rocket fuels and engines adds complexity. Each has unique exhaust characteristics. Kerosene, solid, and methane engines have different impacts. We need a nuanced approach for each launch vehicle. Dedicated research is crucial for understanding rocket emissions. Comprehensive data and analysis are essential for informed decisions. Section 3. A call for transparency and accountability. As the space industry grows, environmental responsibility must be integral to every mission and launch. Transparency is paramount. Space agencies and companies must share data on environmental impacts. Open access to data enables verification, collaboration, and public trust. International regulations and standards are necessary to minimize the environmental footprint. As we reach for the stars, we must safeguard the planet that sustains us. Section 1. The Quest for Cleaner Combustion, RP1, and the Promise of Refinement. Traditional rocket fuels have spurred a search for cleaner alternatives. RP1, a refined kerosene, offers performance and reduced environmental impact. Unlike UDMH, RP1 requires an ignition source, adding safety. RP1's lower toxicity makes it more environmentally friendly. It burns cleaner, producing fewer harmful byproducts. SpaceX and Rocket Lab use RP1, highlighting its performance and environmental benefits. In the quest for a clean-burning rocket fuel, liquid hydrogen emerges as a beacon of hope, offering a future where our cosmic ambitions coexist with a healthy planet. When burned with liquid oxygen, it produces only water vapor, captivating rocket scientists and environmentalists alike. Its combustion produces no greenhouse gases, just pure water vapor. This makes liquid hydrogen the gold standard for clean-burning rocket fuels. However, its use presents unique challenges, requiring large, insulated tanks and specialized handling. Despite these, NASA has long recognized its potential, using it in the Space Shuttle and the upcoming Space Launch System. As we explore rocket propulsion, seeking ways to minimize our environmental impact, a new paradigm emerges, breaking free from traditional chemical combustion. Electric propulsion offers silent, propellant-efficient journeys through the cosmos, leaving behind the fiery plumes of chemical rockets. These systems harness electricity to accelerate charged particles, generating thrust without traditional propellants. From ion thrusters to Hall effect thrusters, they create plasma to generate thrust. Their efficiency allows high speeds with less propellant, reducing launch mass and environmental impact. Moreover, their silent operation minimizes noise pollution, benefiting local communities and wildlife. Electric propulsion excels in space, ideal for long-duration missions like interplanetary travel or satellite maneuvering. As we navigate the complex landscape of rocket propulsion technologies, seeking the optimal balance between performance, cost, and environmental responsibility, we encounter a fundamental truth. There is no one-size-fits-all solution. Each mission, each payload, each destination presents its own unique set of challenges, demanding a tailored approach that considers the trade-offs inherent in every technological choice. For missions requiring brute force, the raw power of chemical rockets, whether fueled by RP-1, liquid hydrogen, or even solid propellants, remains unrivaled. These behemoths, capable of heaving massive payloads into orbit or propelling spacecraft on interplanetary trajectories, represent the culmination of decades of engineering ingenuity and continue to play a vital role in our exploration of the cosmos. However, as our understanding of rocket launch's environmental impacts grows, so too does the imperative to minimize those impacts wherever possible. This means carefully considering the environmental trade-offs associated with different propellants, investing in research and development of cleaner technologies, and exploring alternative launch strategies such as air launch systems that release their payloads at higher altitudes, reducing atmospheric drag and emissions. The quest for a truly sustainable future for space exploration demands a multifaceted approach, one that embraces innovation, collaboration, and a willingness to challenge conventional thinking. By carefully weighing the performance, cost, and environmental implications of each technological choice, we can chart a course towards a future where our cosmic ambitions are aligned with a healthy and vibrant planet Earth. Beyond today's rockets, envisioning a greener tomorrow. As we stand at the precipice of a new era in space exploration, it's crucial to recognize that the technologies that have carried us this far may not define our future among the stars. Today's rockets will give rise to more sustainable, efficient, and environmentally friendly modes of space travel. Our planet's resources are finite, and the environmental consequences of our actions have far-reaching implications. Imagine spacecraft ascending silently into orbit, powered by renewable energy sources. Imagine launch vehicles that return gracefully to Earth, their components reusable. This vision of a greener tomorrow is a tangible goal, achievable through innovation and collaboration. Harnessing the sun. Solar sails and the power of light. Solar sails harness the sun's energy to propel spacecraft across space. Imagine a spacecraft unfurling a vast, shimmering sail, catching sunlight like a sailboat riding a cosmic breeze. The principle is simple. Photons bounce off the reflective surface, propelling the craft. Though each photon's force is tiny, their vast number can propel a spacecraft to remarkable speeds. Solar sails need no onboard fuel, drawing energy directly from the sun. Several successful missions have demonstrated solar sailing's potential. In 2010, Japan's Icaros spacecraft demonstrated controlled solar sail flight. Exploring rocket propulsion technologies, we seek the balance between performance, sustainability, and cost-effectiveness. Hybrid rocket motors embrace the art of compromise. Combining solid and liquid propellant systems, they bridge the gap between power and environmental aspirations. Typically, they use a solid fuel grain and a separate liquid oxidizer. This offers advantages over traditional engines. Throttling the engine provides control and maneuverability. Environmentally, they offer reduced emissions, producing primarily water vapor and carbon dioxide. As technology matures, hybrid motors could enable a sustainable future for space exploration. Balancing our ambition to explore the cosmos with our responsibility to protect Earth is crucial. The drive to push human boundaries is noble, but it must not harm the environment. Rocket launches have real environmental impacts. These are often overshadowed by excitement. We must address these issues. From UDMH contamination to solid rocket emissions, the evidence is clear. Our space endeavors have earthly consequences. We have the knowledge and will to mitigate these impacts. By embracing innovation and sustainable technologies, we can ensure a brighter future for all. The path towards a sustainable space age requires a shift in perspective, recognizing environmental stewardship as essential. It demands a collective effort, transcending national borders and disciplinary boundaries. Innovation drives progress in space exploration. Cleaner, efficient, and less polluting rocket fuels, revolutionary propulsion systems, and reusable technologies are key. Collaboration is essential for complex challenges. Sharing knowledge and pooling resources accelerate sustainable space technologies. International cooperation must define our journey. A shared vision guides our collective efforts. It must reflect respect for all life on Earth, ensuring exploration benefits all humankind. As we stand on the cusp of a new era of space exploration marked by unprecedented technological advancements, let us remember Carl Sagan's words, describing our planet as a pale blue dot in the vastness of space. That's here, that's home, that's us. On it, everyone you love, everyone you know, lived out their lives. Sagan's words remind us of our planet's preciousness and fragility, the only known abode of life in the vast cosmos. As we venture further into space, driven by curiosity, let us carry a deep sense of responsibility for our pale blue dot. Ensure our pursuit of cosmic knowledge aligns with environmental stewardship. Let our advancements address challenges facing our home planet. Strive to become a spacefaring civilization that preserves the pale blue dot. The future of space exploration is in our hands. Let us explore responsibly and innovate sustainably. Collaborate for the benefit of all humankind. Reach for the stars while protecting the pale blue dot. Ensure our journey into the cosmos is one of discovery and preservation, a testament to human ingenuity and our connection to Earth.